Good luck. Hello, everybody, and welcome to the Latin American webinar of physics. Today is a very nice speakers that we're going to have here in this webinar cycle. It's going to be the webinar 141 of since all the story that we have here in the law physics. So the speaker today is Valerie Domcke from CERN, and she got the PhD from the University of Hamburg. And after that, she have done postdoc in CISA in Trieste and in APC in Paris. After that, she was a junior faculty at DESI in Hamburg. And currently, since 2020, she is at CERN. So Valerie, that is here, he's going to talk about the asymmetries in the early universe. And Valerie, welcome to law physics. And you can start your webinar whenever you want. And share the screen.
Okay. Thank you. Thank you for the invitation, for the opportunity, and also thank you for the nice introduction. Okay, so let me tell you about the asymmetries in the early universe, and let me start by telling you what I even mean by these words in my title. So normally, let me first introduce you to the standard law about asymmetries, in particular about baryon and lepton asymmetries in the early universe. So the standard thing that you'll hear is that we know very well the baryon asymmetry, both at Big Bang nucleosynthesis and at CMB decoupling, from the indirect measurements that we have at that time. And from these measurements, we know that at that time, the baryon asymmetry was very small, about on the order of 10 to minus 10. And now in the standard model, B minus L, so baryon number minus lepton number, and B plus L are conserved below the electroweak phase transition. In fact, in the standard model, B minus L is always conserved, and B plus L is conserved at low temperatures, and at high temperatures, we have the spiral processes which drive B plus L to 0. So if you take together this information and you say, okay, well, I know my baryon asymmetry is small, I know that I have a dynamical mechanism that drives B plus L to 0, then you would conclude and say, okay, but then the lepton number obviously also has to be small, right? And it can be at most of the same order of magnitude. So that's kind of where the standard discussion stops, right? The standard conclusion is that any asymmetries in the early universe, so meaning any imbalance between particles and antiparticles, is very small, and in particular is bounded to be of the order of 10 to minus 10. And these asymmetries, this imbalance between particle and antiparticle is directly related to the amount of CP violation that you have in the early universe. So that's the standard story. Now I want to question a bit the hidden assumptions in this standard story, and there are actually quite many hidden assumptions, because there's many caveats to the statement asymmetries in the universe are small. The first caveat is very obvious, right? The first caveat is that the B plus L asymmetry it can easily be much larger at earlier times. And then, okay, we have this dynamical mechanism which drives it to 0 at later times, but maybe at very early times, it could have been very big. And the question is, did that leave any imprint in the evolution of our universe? Then the statement that B minus L is conserved is true in the standard model. Strictly speaking, but as soon as you introduce right-hand neutrinos, which you kind of want to do anyway to give masses to the neutrinos that we observe, you basically automatically introduce B minus L violation. And then again, these statements, as I phrased them above here, are no longer true. So given that, one can then wonder if we have independent probes of the asymmetries in the early universe, which do not rely on these assumptions. Or maybe also probe the asymmetries at different times. And one thing that we can check is the asymmetry in the electron neutrinos, particularly during BBN. So during BBN, we have the formation of the light elements, and the formation of the light elements involves electron neutrinos in order to convert between neutrons and protons. And so changing the amount of electron neutrinos versus anti-electron neutrinos, this is a change to which BBN is very sensitive to. So we can check just from the BBN measurement alone, without making any other assumptions, what is the sensitivity to an asymmetry in the electron neutrinos. And actually, the bound is surprisingly weak. So from BBN, and CMB is even weaker, well, it's at a similar level. So from BBN and CMB observations, without making the assumptions that we made above, we can just conclude that the asymmetry in the electron, which we can parameterize by chemical potential, is smaller than about 10 to minus 2, which is much weaker than the 10 to minus 10 that we had up here. And even that still has a caveat, because this is only true under the assumption that there's only an asymmetry in the electron neutrino and not in any of the other neutrino species. Because if I have asymmetries also in the other neutrino species, then I will have neutrino oscillations, which set in just before BBN. So at the time of BBN, the asymmetries will be relatively evenly distributed among the species. So I can imagine a caveat where I have the total asymmetries in all summed over all neutrino species to be 0, so total lepton number to be 0, but I could still have relatively large individual lepton flavor asymmetries. So I could have large asymmetries, say, in the electron flavor, and then the opposite, but same value, large asymmetry in the muon flavor. And in that case, we could not use this bound at all because the neutrino oscillation would have pushed these asymmetries to 0. And then, in fact, you can check how strong is the bound from BBN on this case, and it's really only order 1. And order 1 here, like telling me that the asymmetry is order 1, meaning the chemical potential over the temperature is order 1, really just means that there's no bound at all, right? Because kind of an asymmetry like this is expansion of the chemical potential doesn't even make any sense if this number is not smaller than 1. So what I want to say here is that despite this kind of standard law that asymmetries in the early universe are smaller, 10 to minus 10, is actually not true, right? Or there's caveats to that statement, and in fact, we can relatively easily construct scenarios where we really have very large asymmetries, potentially order 1 asymmetries in the early universe in individual Fermion species. And it would seem that this scenario is not at all constrained by observation. And that's kind of where my talk is heading today, is kind of wondering, is that actually true? Is it really true that we could have a completely asymmetric universe at early times? And we would not know about it today? Is that really a true statement? And that's what I want to dig into a bit during the seminar. So why is that an interesting question to ask at all? I mean, one, it's simply kind of the question, what can we actually observationally say about the early universe before we go into any model building exercises? Then going to model building, if you have this possibility of having large asymmetries in the early universe, that has consequences for baryogenesis, that has consequences for CP violating BSM physics, that has consequences for phase transitions because large asymmetries tend to change the temperature at which these phase transitions happen. So it has, knowing how large the asymmetries can actually be in the early universe has consequences for a bunch of BSM models. And also, if you want to chase an ambulance, or you can actually even chase 2 ambulances here, is that our recent hints, I would say, from BBN and from CMB, which may point to large asymmetries in the early universe. So that kind of has made this a bit of an urgent question to understand what actually are the observational constraints on asymmetries in the early universe. So the goal of this talk is the following. So I will first talk about a bunch of relatively old stuff, in the sense that I'll tell you about the ingredients that I need in order to make the argument that I want to make. And all these ingredients by themselves have been known for a while. I mean, some of them for a couple of years, some of them for 20 years. So I'll first kind of talk you through all the different ingredients separately that I need. And then I'll put them in the second part of the talk, I'll put them together, and I'll show you how from that we get new bounds on the lepton flavor asymmetries, which will mean that actually what I said beforehand, that we can have these large order 1 asymmetries, will turn out to be not true, because we can, with just standard model physics, we can put a new bound. And I'll also briefly touch upon implications for baryogenesis. Okay. So let's start, as I said, by a couple of ingredients that I need to introduce. And the first ingredient that I need to introduce is the standard model, and in particular, the interactions and the conserved charges in the standard model. So as you probably all know, there's in the standard model above the electroweak phase transition, there's 3 exactly conserved charges. which is hypercharge, and the 3 flavored B- L asymmetries. But if we go to really the very early universe, on top of these exactly conserved charges, we have approximately conserved charges. So what happens is that as we go higher and higher in temperature, means we go to faster and faster expansion rate of the universe. And at some point, the different interactions, meaning the Yukawa interaction, the Svalaron process, cannot keep up with the expansion of the universe. And so what this plot on the right indicates is the different standard model interactions as a function of the temperature of the thermal bath when they come into equilibrium, meaning when they become efficient. So at very high temperatures, barely no interaction is efficient. The top is the first to actually become efficient compared to the Hubble expansion rate. And then over many orders of magnitude, all the standard model processes become efficient until the last one, which will be an important one, is the electron Yukawa, which becomes efficient at about, or we say it comes into equilibrium at about 10 to the 5 GeV. So that means that at any given point in this diagram, I can basically separate my conserved charges, or sorry, my effective interactions from my ineffective interactions. And for every ineffective interaction, it means I get an additional conserved charge, or at least an approximately conserved charge. And the limit that interaction is 0, it means I turn off an interaction, meaning I have an additional conserved charge in the system. So this just means I can rewrite this plot as a simple linear algebra system, telling me kind of which efficient interactions relate to different charges, and which charges, on the other hand, are conserved. So concretely, here, what I'm showing here is for different temperature regimes going from cold to hot. We here have the different interactions, all the different standard model interactions, and the check mark indicates that the interaction is efficient. So at 10 to the 5 GeV, everything except for the electron Yukawa is efficient. And every time when something is not efficient, right, instead of the check mark, I write the corresponding conserved charge. So as we go up in temperature, we get less check marks, so less interactions are efficient, and we get correspondingly more conserved charges. And this is really just a linear algebra system, right? So the number of conserved charges plus the number of linearly independent equilibrated interactions has to match the number of total number of particle species, which is 16 in the standard model. So what this means is that if I start at high temperatures and I put by hand some asymmetry into one particle species, then I need to kind of crunch my linear algebra system. And this asymmetry that I put in one species will, following the constraint equations that I have in the system, will be distributed among other charges in the system. And then as the temperature evolves, as different interactions become efficient, there will be a constant reshuffling of the charges that I put in. This is really just the standard model at work. Okay, that was the first ingredient. The second ingredient that we need is the so-called chiral plasma instability. So this is an effect in chiral magnetohydrodynamics. So the system that I'm studying here on this slide is I have a hypergauge field, so U1y. I have a thermal plasma of particles, and I will allow for asymmetries in these particle species. So I will allow for chemical potentials. And I'm describing this in a very coarse-grained way, hence the word hydrodynamics, right? So this is really an effective theory. I'm not tracking the individual particles, but I'm really describing this as a fluid. So how in this MHD, how this works is you basically couple classical Maxwell's equation with an effective current, which sources these classical Maxwell's equation. And this effective current has the term you would expect, which is conductivity times electric field. That's just the standard Ohm's law current that you would expect. Then the current also has a contribution which is sourced by the velocity of the plasma and the magnetic field, right? You can imagine if I have a magnetic field and I have the velocity and just the Lorentz force, right? And that will give me a current. So this is basically what this term is telling you. And then finally, we have this last term, which is called the chiral magnetic effect. So this is a contribution to the current, which is proportional to the chemical potentials, a particular linear combination of the chemical potentials, which is called the chiral chemical potential. But basically, what I'm doing here is I'm summing over all the chemical potentials of all my particle species. And the prefactor here is the helicity the multiplicity of that species and the hypercharge of that species squared. So this is the definition of the chiral chemical potential, which enters in this equation. And this current here is proportional to the magnetic field. Now, that is maybe a bit surprising, right? I mean, normally you think currents are, you understand, normally currents are proportional to the electric fields, right? Or currents via the Lorentz force, right? Come with a cross product with the magnetic field. But here we have a contribution to the current, which is parallel to the magnetic field, right? So that might at first seem a bit unusual, but what's actually going on here is that this is the chiral anomaly equation. This is how the chiral anomaly equation appears in an effective theory of Maxwell's equations in this kind of fluid type description. Okay, so this is the effective current. Now we plug this into Maxwell's equations. And now I'm going to, in the first step, just for this slide, I'm going to neglect this term here, going to neglect the fluid velocity. And then you get a closed system of equations which contains the helicity, meaning basically the magnetic field here, the energy in, so this is the helicity of the magnetic field, the energy density of the magnetic field, and then also I will have an equation for the chiral chemical potential, which I'm not showing here. But just to look at the two equations for the magnetic field, or the hypermagnetic field. So eta here is just a conformal time. And in both cases, you have, and I'm doing this in Fourier space, so hence the index k. So the first term in both cases is the diffusion term. So this is what you expect. Or you expect that I have a plasma, and at small scales, diffusion is efficient, meaning I will have some term which comes with a minus sign, so it tends to erase whatever is there. And it comes with a k squared, indicating that it's particularly efficient for small scales. Then, however, due to this chiral magnetic effect, I also have a second term here, which is proportional to this chiral chemical potential. And now, depending on the sign of the chiral chemical potential, right, which can have either sign, depending on the asymmetries that I put in the beginning, this term can have the opposite sign as the term in front. So what that means, if you solve this equation, these are coupled equations, right? But you can rewrite it as a just an evolution equation with a effective mass matrix, and for each possible sign, for each of the two possible signs of the chiral chemical potential, there will always be one mode which can become negative, where the effective mass squared term can become negative. So we can have one of the helicity modes, which in a certain range of k modes, so in a certain range of scales, below, like, so scales above a certain value, meaning k values below a certain value, given by the chemical potential, they become tachyonically unstable, right? And tachyonically unstable, again, means that they have an effective negative mass squared. So what this means is that you get, if you have a system where you have a non-zero chemical potential, you can get an exponential growth of magnetic fields. And this is the chiral plasma instability, right? So the name instability comes from the fact that you have here something which is a negative mass squared. So you get an exponential growth of the corresponding gauge field. And so we can now estimate how much gauge fields we can produce in this way. For that, we'd actually need the second equation that I'm not writing here. So there's also an evolution to close the system. We need to also know how this mu y5 evolves, right? And this mu y5 just evolves according to the chiral anomaly equation. So the change in the chemical potential is just given by FF dual, so basically by the helicity. So when you plug all of that in together, what you understand is that as long as this chiral chemical potential is non-zero, it will source this tachyonic instability. So what happens is that whatever chiral chemical potential you have in the beginning, it will be completely converted into helical magnetic fields. And this is given by this relation here. So these factors of temperature and alpha, so alpha is the hyperfine structure constant. And this is roughly an order 1 factor. They just come from these coefficients in these equations, but basically, and dimensional analysis more or less, but essentially this chiral chemical potential will be this initial chiral chemical potential will be fully converted into helicity. And because we can see here, we have a differential equation. From this differential equation, we can extract a timescale at which this conversion will happen. And this timescale we can convert into a temperature, which is what I'm giving here. So this temperature, the CPI temperature, is the temperature at which this process becomes efficient, so at which we convert the chemical potential into helical magnetic fields. And this temperature is given by, okay, here we have just some constants, which are the standard model values. But importantly, this temperature is proportional to the chiral chemical potential squared. And for values of the chiral chemical potential of around 10 to minus 3, we find that this CPI temperature is about 10 to the 5 GeV, which is the value at which the electron Yukawa comes into equilibrium. And that will be important in a second. So we learned on the previous slide that if I put a particle, if I put an asymmetry somewhere in my system, it will be redistributed across all the particle species. And now we see that this asymmetry can moreover be converted into helical magnetic fields. Okay, then this is the second to last ingredient. So this is the inverse cascade. So in the previous slide, I neglected the fluid velocity. I did that because if I put in the fluid velocity back, right? So this Maxwell's equation is a priori a linear equation. But if I include this fluid field, which is in turn sourced by electric and magnetic fields, the system becomes nonlinear, and I can no longer solve it with linear methods. But of course, reality doesn't care about that, right? So in reality, we have this fluid velocity. So we have to think about what happens if I put this fluid velocity back in the system. So what I said on this slide is kind of all true as long as this fluid velocity is small, which is initially typically the case. But then eventually when this process starts, when I have this chiral plasma instability, I generate large magnetic fields. They in turn source this velocity, and hence eventually I will come into the case where I need to take this into account. However, this fluid velocity, it does not only make life complicated, it also has a very interesting effect, and that is called the inverse cascade. So what the fluid, as I said, this fluid velocity term introduces nonlinear mode couplings, which means you can now transform energy from one mode of your gauge field into another mode. And now just from thermodynamics logic, without even solving any equations, you know that the system will want to go into a status where it minimizes its free energy. So we'll want to conserve helicity, because helicity is an approximately conserved quantity in the system. So we'll want to conserve helicity, but minimize energy. And the way you do that is that you go to very long wavelength modes, because long wavelength modes have the minimal energy per unit of helicity. And this is the inverse cascade. So the inverse cascade basically tells you that as soon as this fluid velocity becomes efficient, becomes large, you can convert, you can kind of push your energy and push your helicity to very large wavelength modes. And this is something, okay, this is now very kind of hand-wavy argument, but people, in particular these authors here, have simulated this in great detail on the lattice, where of course you can account for all these nonlinear actions. And this is indeed what they find. So they find that as soon as your magnetic fields are above a certain threshold, which in turn then triggers a large fluid velocity, this inverse cascade is triggered, and the helicity is pushed to very large scales, which means it's protected from diffusion, because diffusion was only efficient at small scales. So we saw previously, the asymmetry can be distributed among different particle species. It can be moved from the particle species into the magnetic field. And now we see that once it's in the magnetic field, it can be pushed to very large scales, avoiding diffusion, and hence it can survive for a very, very long time on cosmological timescales. Okay, and then the last ingredient that we need is that if this magnetic field survives until the electroweak phase transition, then we get a source of baryon asymmetry. And the reason for this is basically the chiral anomaly, so the ABG anomaly, which on the left-hand side of this chiral anomaly, you have the change in baryon number or lepton number. And on the right-hand side, you have the helicity of the magnetic fields. But now what happens at the electric phase transition, and here I'm talking about a completely standard crossover electric phase transition, is just because you project from hypercharge to electromagnetic charge, you're changing the Chern-Simons number associated with the magnetic field. You're associated with the massless U1 field that you have in your system. And that means you're changing one side of this anomaly equation, But that means, because the anomaly equation always has to be true, that you also have to change the other side. Right, so this is a kind of very high level view how to see that if you just have helical hypermagnetic fields present at the electric phase transition, that will have to lead to a B plus L asymmetry produced during the electric phase transition. Now, you're producing this at the electric phase transition, which is precisely the point in time where the sphalerons decouple. So if you produce this asymmetry much earlier, you wouldn't care because the sphalerons would just wash it out. But now you're producing it just at the time when the sphalerons are decoupling. So there will be a competition between a source term, which is driven by these helical fields, and a washout term, which is driven by the sphalerons. And this competition is encoded in this prefactor here, which I'll talk about in a second. But up to this prefactor, which really depends on the details of how exactly the electric phase transition happens, this means that the entire helicity present, well, up to some order one factor, the entire helicity present at the time of the electric phase transition gets converted into a baryon asymmetry. Now we can use so here, now I'm just plugging in some numbers. So this term, as I said, it depends between the competition of the source term and the washout term. And there's actually some significant theoretical uncertainty on that. I would say plus minus 1-2 orders of magnitude, at least. But taking the kind of the central value for this number and just plugging in the constants here, we see that we expect to get a baryon asymmetry, which is about 10 to minus 6 times the helicity in units of temperature. And then we use the previous expression, how we related the helicity to any initial chiral chemical potentials. And we see, so this was, just to remind you, this was this expression here. Now just plugging in some numbers. And I get a factor 10 to minus 4 here. Meaning, if I have really order 1 chemical potentials, this equation tells me that I expect a baryon asymmetry of order 10 to minus 4, right? Which would be ginormous, completely going against observations. So this is kind of the logic of what I'm going to be presenting in a second, right? So as soon, what the take-home message here is, as soon as you have chemical potentials which are larger, or particle asymmetries which are larger than 10 to minus 6 at any early time in the universe, right? It can be way before BBN, way before CMB. Then this equation tells you that you are at least in danger of massively overproducing baryon asymmetry. Now, and that's to be contrasted with what I told you beforehand, right? That I was saying beforehand that kind of current bounds basically telling you can have order 1 asymmetries and there's no constraint, right? So here we're seeing, okay, once we actually take all these different ingredients together, there potentially is a constraint. So let's have a closer look at this issue. So just to recall the ingredients that we have so far, right? So far we said, okay, standard model interactions reshuffle particle asymmetries. The chiral plasma instability converts these asymmetries into helicity. Then with the inverse cascade, this helicity can survive until the electric phase transition. And at the electric phase transition, it can generate a potentially large baryon asymmetry, potentially in contradiction with observations. Okay, so now let's use this concretely to actually now set bounds on asymmetries in the early universe. So the situation, so the situation I want to focus on, just for simplicity, is the temperature range just above the equilibration of the electron Yukawa. You can also do this in any other temperature range, right? And you can also look at any other combination of asymmetries. But let's, for some simplicity, this is the simplest case, let's focus on that. So I can compute the chiral chemical potential at that point, right? This is just the formula taking into account the hypercharge and the multiplicity of the particles and all the interactions that are efficient or not efficient. And this is what I get, right? So there's, at that time, there's 2 exactly conserved charges in the standard model, which are there's 3, right? The 3 B minus L asymmetries. And here, because they come with the same coefficient, I've combined them, right? So this is the B minus L asymmetry in the electron, and this is the B minus L asymmetry in the muon plus tauon. And then I have 1 approximately conserved charge, which is the electron itself, the right-handed electron. In principle, of course, I also have hypercharge, right? But I set hypercharge to 0 because I do want an electrically neutral universe at the end. Okay, and now importantly, we see that the coefficient in front of the electron, B minus L, and in front of the mu plus tau B minus L is not the same. And the reason for this is obviously that the Yukawa couplings associated with mu and tau are in equilibrium, and the Yukawa coupling, that this chiral plasma instability happens before the electron goes into equilibrium. Because once the electron goes into equilibrium, this equation no longer holds. And in fact, then once all the standard model actions are in equilibrium, the interactions then dictate that this chiral chemical potential is always zero. So I can only have this chiral plasma instability above this temperature. Once kind of the would-be temperature falls below this value, it just means it just doesn't happen. Okay, so that's one condition, but I gave you the formula for the CPI, right? So this temperature formula somewhere here, right? And we saw this is why it shows this benchmark value, right? And now we see it was proportional to mu squared over 10 to minus 3. So clearly I need to, in order to have this temperature above this value, I need mu5 above this value. So going back to now our concrete example, I plug in the numbers, and I find, as you would have just expected by looking at the previous equation, that I can, the chiral plasma instability happens if and only if the chemical potentials in the individual B minus L flavors are above 10 to minus 2. So that's one condition. And then the second condition is, okay, let's actually overproduce baryon asymmetry, right? So now let's actually compute this baryon asymmetry, right? So this is this expression here. I plug in the numbers here. And I get, okay, we overproduce if this value is larger than 10 to minus 5. So clearly, this is the stricter constraint, right? So the statement here is, if the chiral plasma instability happens, meaning if the chemical potentials are above 10 to minus 2, then we massively overproduce baryon asymmetry. We overproduce baryon asymmetry by several orders of magnitude, right? Which is also why we don't have to care in great detail about this uncertainty in the Valerie processes and the production of this asymmetry, right? Because we massively overproduce. As soon as we hit this threshold, we overproduce. So the conclusion from here is that this is the bound one should consider, and that we cannot actually have order 1 asymmetries in the flavors, in order 1 flavor symmetries, but as soon as the flavor symmetries are bigger than 10 to minus 2, this is actually ruled out from just our observation of baryon asymmetry. So this is a bound which is 2 orders of magnitude stronger than the BBN bound for this particular case of a B minus L symmetric universe. Okay, because it's such a nice result, I put it again. But let me talk a bit about the implications of this. So as I said, right, so this bound always applies independently of if B minus L is non-zero or 0. If it's non-zero, the bound is of similar strength than the bound that we already had from BBN just on the electron neutrinos. But it applies in a completely different temperature range, and it's derived in a completely different way. So in that case, it's just an independent bound, but of a similar strength. But in this particular case, the B minus L is 0, then actually it's a factor 100 stronger than the previous bound. It applies, the previous bound applied at BBN temperatures, right, or at CMB temperatures. This applies at temperatures larger than 10 to the 5 GeV, right? So it's really a constraint on the primordial symmetries. So even if you have larger symmetries, which are then washed out over the course of the universe, and they're completely washed out by the time you get to BBN, then BBN will tell you you have no problem. But here, yes, you could still have a problem, right? So even asymmetries which are only present in the early universe and then get washed out via this mechanism, because we kind of hide the asymmetry in the magnetic field in which it's very well conserved, that can still cause issues by overproducing baryon asymmetry. Then now the helium anomaly that I was mentioning, so the BBN anomaly, suggests, right? I mean, so it really suggests is maybe even a slightly too strong word, right? So this helium anomaly keeps on coming and going every 5 to 10 years, right? So not sure how seriously one should take it, and I'm not an expert on the observational data here. But if you take it seriously, the simplest explanation to explain the data at face value is to introduce an asymmetry for the electron neutrinos. And that would require an asymmetry of 4 times 10 to minus 2, which is slightly above the bound that we put, right? So I would at least say we disfavor this explanation. However, there's a caveat, right? Because here you need this asymmetry at the time of BBN. We only put a constraint at temperatures above 10 to the 5 GeV. So if you generate this asymmetry below 10 to the 5 GeV, we have nothing to say on it. So that I'm not saying that it's completely impossible to explain the helium anomaly with chemical potentials, but I'm saying if you do want to explain it with chemical potentials, you have to make sure that you generate them below 10 to the 5 GeV. This bound also disfavors some models of lepton-flavogenesis, where the idea is that you have large asymmetries in the individual flavors, and then they basically leak slightly into some final total B minus L asymmetry. But for that, you need large initial asymmetries in the individual flavors, and that again is in tension, at least with this bound. You can, of course, you can, like, I talk about bounds, right? Because I think that's the most robust thing that you can do with this result. But you can, of course, always play the game and say, okay, well, if I have one region of parameter space where I massively overproduce, and then I also have another region of the parameter space where I obviously underproduce, where just if I take this asymmetry to 0, so there has to be, physics is continuous, right? So there is going to be some regime when I'm just marginally satisfying this bound, where I can theoretically use this to get the correct baryon asymmetry. Now, it's probably going to be a pretty horribly fine-tuned model, but in principle, you can think about building baryogenesis models in this way. This I already mentioned, right? So the result here is very sensitive to the exact dynamics of the chiral plasma instability, but is less sensitive to the dynamics of the electric phase transition, because as soon as we trigger the CPI, we are pretty confident that we massively overproduce. And on a more conceptual level, what we're actually doing here is if you think where our bound on B minus L violation comes from, or our bound on B minus L violation comes from combining our knowledge about sphalerons, which violate B plus L, with the observed baryon asymmetry. This is kind of the standard how we constrain total B minus L. And now what we're doing here is conceptually actually very similar, but instead of using the non-perturbative SU2 processes, we're using the non-perturbative U1Y processes, meaning the CPI. So if you combine these processes again with the observed baryon asymmetry, you get a bound which is again a bound on a linear combination of chemical potentials, but it's not the linear combination which is B minus L, it's a different linear combination. Here I'm using it to constrain the flavored B minus L asymmetries, but you can use it to constrain whatever, right? I mean, it's just a bound on some particular linear combinations depending on the temperature of chemical potentials. Okay, so that was the first 2 points, which is actually what I wanted to spend most time on. Let me just more briefly talk about possible implications that this could have for baryogenesis. And the first model I want to start with is this Axigenesis model. So in the Axigenesis model, the idea is you have an axion-like particle, which is rotating very rapidly in some sort of Mexican hat potential. So you start at large field values with a large initial velocity, and you're kind of zooming around until then finally you go down and you land in the rim of the hat, but you're still going in circles. And then eventually at the QCD phase transition, a kind of little QCD potential will show up here at the rim of the hat. And then you get back to that's when you kind of start producing axion dark matter and these things. So you can get in this the model here is that you can have two interesting consequences of this. So one, you can produce once you're in the rim of this hat, and once a QCD potential appears, so at the QCD scale, you can produce axion dark matter via the kinetic misalignment mechanism. So it's called kinetic misalignment because you have this high velocity in the game. But you can also, because you have this axion-like field, which is rotating very fast, which means it acts as an effective chemical potential to the fermions in a game, you can also generate baryogenesis through this mechanism of spontaneous baryogenesis. So simply through the coupling of the different fermion species to this rotating axion field. This model is very simple because all you do is add an axion-like particle with a specific initial condition. And then in principle, you solve two problems. You solve axion dark matter, you solve baryon asymmetry. However, in the simplest model, you can't get both. Simply quantitatively, you cannot, right? So either you get the axion dark matter right, but then you underproduce baryon asymmetry, or you get this right, but then you overproduce dark matter. there's ways to fix that, right? But in the simplest model, this is the story. This model has two regimes. Here up here, right, when you're before you settle into the room and once you settle into the room. And what is important for our purposes is that as soon as you have this rotating field, that's a degree of spontaneous CP violation, right? It induces chemical potentials in all the particle species, and hence it can trigger the chiral plasma instability. And if this rotating field, this really is supposed to continue for a very long time, right? It's supposed to continue rotating all the way down until the QCD phase transition, because otherwise it can't generate the axion dark matter. So that means, contrarily to what I discussed beforehand, right before, and I said, okay, let's put some God-given chemical potentials in the early universe and see how things evolve. Here I have an active source term all the way down to the QCD phase transition. So I can, in principle, trigger the CPI now also below this magic number of 10 to the 5 Jeff, just because I have an active source term in the system. So this makes us think that, okay, here this model definitely is one of the models that are at risk of triggering the chiral plasma instability. So we expect that there should be constraints on the parameter space from the fact of not overproducing baryon asymmetry. So that's what we did. So we distinguish two phases, right? So first at high temperatures before the settling temperature, we're in this inspiral phase, and then below the settling temperature, we're in the local minimum of the Mexican hat. The dark matter production happens around the QCD scale, which will be lower than this settling temperature. And the amount of axion dark matter that you produce is just directly proportional to kind of the initial velocity of the field that you put. The chiral plasma instability, on the other hand, is most efficient at early time, so before the settling temperature. And I can use the formulas I was showing you beforehand to compute the CPI temperature for this particular model. And we can, the goal now is, so previously I said we can avoid the CPI if we go to temperatures below the equilibration of the electron Yukawa. Here it's slightly different, right? Because the electron Yukawa temperature doesn't actually matter because we have this active source, but we can avoid the CPI if we go below this settling temperature. But if we're above the settling temperature, the CPI will happen. And then what we find again is similar to what we found previously. Once a CPI happens, it's just so efficient that it tends to just overproduce the baryon asymmetry in the entire parameter space. So the constraint that we will set is basically this condition here. Does the chiral plasma instability happen before this field settles into the rim, or does it not, right? And if it happens before, that parameter space is going to be dead. And if it doesn't happen before, then you're safe. And this is what this looks like in this parameter space of this model. So here you have the axion decay constant and the mass of the radial degree of the Peccei-Quinn field for some particular axial model, right? In this case, the supersymmetric KSVZ model. And the white parameter space is the allowed parameter space. This green constraint and the purple constraint are constraints which were already previously known. And now our new constraint from the overproduction of the baryon asymmetry to the CPI is this red region here. So as expected, you find that part of the parameter space is going to be excluded, which tells you, that there are models out there which were not invented with this in mind, right? But were invented just to do baryogenesis. But in part of their parameter space, they automatically come with such large chemical potentials, such large CP violation, that they actually violate the bound that we put. And again, in principle, you can play this game, right? And say, okay, if you're exactly on the boundary of this line, then in principle, you get the baryon asymmetry exactly right. But it's going to be a very fine-tuned situation. But given that this model kind of shines because it's very minimal. So here you can, for a careful choice of your parameters, you can with a very minimal particle content, right? Meaning just an axion-like particle, nothing else, but very specific initial conditions and very specific parameter choice. You could in principle get both dark matter and baryogenesis right. So you'd have a fine-tuning problem. You definitely have a fine-tuning problem. But in principle, you can do it with a very minimal particle content. Okay, I think I'll maybe stop there. Leave a bit more time for questions. So let me jump to my summary. So what we saw is that any spontaneous CP violation in the early universe, be it by chemical potentials that I put by hand, right, or that I put by some pre-baryogenesis mechanism that I put, for example, by gut baryogenesis. So these types of chemical potentials, or also some rotating field which violates CP, all these types of spontaneous CP violation, they can trigger this chiral plasma instability, which then, together with the inverse cascade, leads to a production of baryon asymmetry. That can be good, that can be your model of baryogenesis, or it can be bad because it overproduces. And using this, we set a new bound on the primordial B minus L conserving lepton flavour asymmetries of the order of 10 to minus 2. And we also see that we can get constraints on this Axigenesis model, or more general constraints on the axion kinetic misalignment mechanism. But in a broader sense, I mean, I really just see this as both things that I explained. I basically see just as examples, right? Because the framework that we're using here is, I think, much more general. The framework tells you if you have any model which is any sort of large asymmetries in the very early universe, then you can use this to put constraints and to potentially constrain part of your parameter space, or maybe also turn it into a viable baryogenesis model. Okay, thank you.
Okay, thank you very much, Valerie. So we're going to start with the question. We have a couple of questions in the YouTube channel. So in the meantime, just remind to the people that you can follow us in the YouTube channel. Just to click the subscribe button to keep updated with the latest webinar that we are going to be programming during the year in this season. So let's start with some questions. I don't know if there are questions from the audience here. Alejandro has a question, please. Go ahead.
Thank you, Valerie, for this very nice talk. I come from a very different field, so my questions are perhaps more conceptual. So if my question is too naive, please apologies. Is there a way to understand physically that efficiency versus like how many charges do you have? I think, like you said, like less efficiency means you have more charges. Is there a way to understand this?
Yes. So just imagine, here, this is what you're talking about, right?
Yeah.
Right. So imagine you have a linear algebra, a system of equations, right? And you simply have a number of equations, right, which linearly relate your charges and set them equal 0. Right, so basically, I don't know, an interaction involving, I don't know, a Higgs turning into, well, whatever. Let's say a neutrino going to a Higgs lepton doublet, right? That written as an equation would mean chemical potential of the neutrino minus chemical potential of the Higgs minus chemical potential of the lepton doublet equals 0, right? So very, very simple type of equations. So just it's going to be some linear combination of my chemical potentials equals 0 when that interaction is efficient. And the more interactions are efficient, the more equations you have, simply. And if the interaction is not efficient, you just remove that equation from the system. And now you have a fixed number of particle species. And now the number of equations that you're imposing in your linear algebra system is changing. And simply the fewer equations you have, right, then the system is under constraint, and you just have more parameters, in this case, more chemical potential that you can just freely choose. And something that you can freely choose is, in this language, a conserved charge. I see.
Okay, but so my second and last question then related to this, I was trying to think about this exactly, is, you know, like these chemical potentials in some sense are associated to something that a number density of something in some sense.
Right,
but then
here,
does
right?
It mean that that doesn't mean that the chiral charge is conserved? And if that's not the case, then this chiral potential is it really a potential? I don't know. Sorry, this is not well posed question. So I guess my question is more about the origin of this Chiral potential, if it's associated to a Chiral charge, and if this is not conserved, or if it is. Is this
okay. Okay. So the chiral chemical potential is a linear combination of the chemical potentials of the individual charges, right?
Okay.
And these chemical potentials are only conserved in this manner, right? So they're only conserved within a given temperature regime, right? So say I'm here 10 to the 8 GeV, right? Then I have a set of interactions which are completely efficient and a set of interactions which are completely inefficient. And as long as I stay in that regime, all the individual chemical potentials are conserved, and hence also the chiral chemical potential is conserved. But then when I cross one of these lines, I add a new interaction into the game, then all the individual chemical potentials will change, and correspondingly also the chiral chemical potential will change. So every time you cross a threshold here, you kind of will go down, like it will be some sort of step function type function.
I see. Okay. Thank you.
So before that, if there are other questions for the audience here in the Zoom session, we have a question from YouTube from Adila Afzal. He said, "Hi, thanks for the very nice talk. Can you please comment that during the process of Axigenesis, do we have the domain wall problem?"
That's a very good question, right? So here, okay, so with the domain wall problem, right, it depends when you break the Petri-Quinn symmetry associated with the axion potential versus inflation, right? So that's always the story. So in this case, the idea is that we first have inflation. What? Sorry. So the idea here is that here we have we never restore the Petri-Quinn symmetry, right? So let me go to the plot. Right. So here we never discuss the situation where the PQ symmetry is restored, right? We always really just work in the picture where the PQ symmetry is already broken, right? And in that, and so kind of our initial conditions are really when we start outside here in the rim of the Mexican hat. So in that sense, so I don't think we have anything new to say on the domain wall problem here, right? So it depends, of course, on the number of domain walls, and it depends how you align, how you do the time ordering, right, of inflation and this mechanism. But we don't have anything new to say on the issue here.
Okay, thanks. Later, maybe Adila is gonna say some comments about or something like that. Okay, I don't know if there are other questions. I have a question about when you were discussing about the role of action in the mechanism of the Axigenesis, let's say. What would be also the possible role of other type of pseudoscalar particles in this scenario? I mean, is it possible to generate the same asymmetry with a, let's say, baryon related with the lepton charge, or the role of other type of action in granulified theories or something like that?
Totally, right. So I think so from the point of view of generating particle asymmetries, and then from the point of view of potentially triggering the chiral plasma instability and so on, right? It doesn't have to be the actual QCD axion, right? I mean, then I think this goes to, I mean, then if you have any particle, right, then you have to specify how exactly you want to couple it to the standard model particles, and your constraints will depend on what those couplings are. But that is not at all specific to the QCD axion. I think what is nice here is the motivation to use the QCD axion is then, okay, you'll kind of get the dogmatic for free, and you also solve the Petri-Quinn problem, right? But that's really just out of minimality. All the more conceptual questions of generating an asymmetry and how does asymmetry propagate through the different phases of the universe, you don't at all need this to be the QCD accent for that.
Okay, thank you. Yeah, just the okay. Yeah, the idea of I understand that the best scenario is to talk with the minimal, to start with the minimal setup with the standard model, of course. So I don't know if there are other questions. In the Adila, he said thank you to you for the answer. So, I don't know, Joel, if you have a question.
I also have a naive question. So in principle, so here you're assuming standard cosmology, right? But if you assume a non-standard cosmology, and Roberto will laugh because we've been discussing this elsewhere. If you have like entropy injection, right? Could that decrease your bound? If you have like a scalar that will decay, some matter domination part that will decay into radiation, could that decrease your bounds? Relax your
right. So okay, so in principle, okay, let me first answer in the more general way, right? So let's forget about Axigenesis and just kind of talk about this bound here, right? So here in principle, yes, right? Because I mean here we're saying we're overproduced. The problem is we're overproducing baryon asymmetry, right? So of course that's a problem you can try and solve by entropy injection. Though you do need to kind of check how the scaling of everything goes with temperature, right? Because it's all the same thermal band, right? Because then like you'll be, because then you have to see is this actually, I mean, then you what I'm saying is you also have to take into account the entropy injection when you discuss, of course, how the asymmetries evolve over time, right? So there's kind of going to be the actual asymmetry in the early universe, and then there's going to be kind of the asymmetry at later times, and you need to connect the two, right? But so, but definitely depends, right? Definitely here we're assuming standard cosmology, right? And if you have entropy injection, that would change the picture. And in fact, in the Axigenesis model, it comes a bit automatically, because in the Axigenesis model, you can have a phase of matter domination and inclination domination. For doing that calculation, we had to actually go beyond the standard cosmology, right? And really check explicitly the evolution of the quantities and really check explicitly through the different scaling regimes how the bound asymmetry evolves.
Okay, I'll think about that for a while. Thank you very much.
Okay, so okay, in YouTube we don't have any other question. I guess also for the time of for the length of to keep consistent with our previous webinar, we are gonna start finishing here the webinar. So first of all, thank you very much, Valerie, for the webinar. It was very interesting. So, and for all the people that are following us in YouTube, you can, of course, you can explore our YouTube channel and check the previous webinars, and also to continue to assisting to this, to attending to these webinars in the future. So I hope everybody is going to be fine, and see you in the next time in this law physics webinar.